I have a bit of a confession to make.
Okay.
You know those flight tracking apps? Flight Radar 24, Flight Aware?
Oh, I know them well. They're dangerously addictive.
Right. Well, I found myself just staring at one the other night. I was supposed to be working, but instead I was watching this tiny little plane icon just crawling across the Pacific.
Mm-hmm.
And so I decided to zoom out, like really zoom out, to see the whole world at once.
Okay.
And when you do that, you notice this incredible, almost chaotic web of traffic in the Northern Hemisphere. It's like a spider web of light.
It is.
You've got planes crossing the Atlantic, planes crossing the Pacific, and a surprising amount of traffic cutting right over the Arctic Ocean.
Yeah, the polar routes.
To get from, say, New York to Dubai or London to Tokyo, it is just busy up there.
It's the highway of the sky.
Absolutely. But then you scroll down, you look at the bottom of the world, and the contrast is just jarring. There is this massive, conspicuous circular void right over Antarctica. It's not just quiet, it's empty.
A blank spot on the map.
It looks like a force field. You see these long-haul flights, Sydney to Santiago or Johannesburg to Auckland, and they're curving around it.
Curving the edges.
Yeah, they're hugging the ocean, but they almost never cut through the middle. And I think the natural assumption for a lot of people, and me too, is, okay, what aren't they telling us?
Right.
Is it some kind of political no-fly zone? Is it secret military airspace? Is it
aliens?
I can essentially guarantee you it is not aliens.
Okay, good. That's a relief.
And strictly speaking, it's not a political ban either. There is no treaty that says thou shalt not fly here.
So that's the mission for this deep dive then.
Yeah.
We're going to unpack the engineering, the meteorology, and the absolute logistical nightmare that keeps commercial aviation away from the South Pole. And I've got a stack of sources here that is frankly intimidating. We're talking civil aviation regulations, safety data from NASA's ARCERA system, logistics reports from the Australian Antarctic program, and even mass rescue operation manuals from COMNAP, which is the Council of Managers of National Antarctic Programs. Some light reading.
Very light. But to help me make sense of it all, we have you. And I think it's important to frame your perspective here. You aren't just looking at this as a researcher.
No.
You're looking at this as a commercial pilot and a logistics specialist.
That's right. And I think the best way to frame this whole discussion isn't as a ban. Nobody is standing at the 60th parallel south with a stop sign. It's a calculation.
A calculation.
It is a brutal, cold calculation of extreme risk versus, well, very little reward.
Okay, a calculation of risk. I like that. But surely with modern planes, we have the Dreamliner, the A350, these incredible machines. Surely we have the tech to fly over a block of ice.
We absolutely have the technology to fly over it.
Yeah.
The problem is when you might have to stop flying and start landing, or, when things go badly wrong.
Right.
We're going to look at this through what safety experts call the Swiss cheese model.
The Swiss cheese model? Okay, I've heard of this. It's the idea that accidents only happen when the holes in the cheese all line up.
Exactly. Imagine a stack of Swiss cheese slices. Each slice is a defense layer. You got weather forecasting, fuel technology, legal regulations, rescue capabilities, and so on.
Got it.
Usually the holes in the cheese are in different places, right? So if a threat gets through one layer, the next solid bit of cheese stops it. But in Antarctica, the holes are massive and they align almost perfectly.
So it's not just one thing stopping flights.
No.
It's a combination of weather, physics, legal rules, and the terrifying reality of what happens if you crash.
Precisely. It's a perfect storm of hazards all in one place.
Okay, let's unpack this layer by layer. Section 1, the geometry of the globe. Why do we fly north but not south? Because just looking at a flat map, if I want to go from, say, Perth, Australia to Buenos Aires, Argentina, it looks like I should just go straight across the ocean.
Right. But the world isn't flat, as we know. We have to start with the concept of great circle navigation. This is really Aviation 101, but it breaks people's brains a little bit because we are so used to those Mercator projection maps.
The ones where Greenland looks the size of Africa?
Exactly. On a sphere, the shortest distance between 2 points isn't a straight line, it's an arc. It's a curve.
Okay.
If you take a piece of string and stretch it tight between 2 points on a globe, that's your flight path. That's the Great Circle route.
And in the Northern Hemisphere, this works out great for us, right? This is why planes fly over Greenland to get from the U.S. to Europe.
It does. Think about the economic geography of the planet. I like to call it the dinner table of the North.
The dinner table.
You have the major economic powerhouses, North America, Europe, and Asia, all arranged in a rough circle around the Arctic Ocean. They're the guests at the table. So if you want to pass the salt from New York to Hong Kong or from London to Tokyo, the shortest reach is directly across the table.
Over the North Pole.
Exactly. It's the shortcut.
So the demand is there, and the geometry works. Crossing the Arctic saves hours of time and thousands of gallons of fuel. It's a no-brainer.
It makes complete economic sense. But the Southern Hemisphere is different. We often call it the water hemisphere for a very good reason.
Right. It's mostly ocean.
It is. And the major land masses, Australia, Southern Africa, South America, are incredibly far apart. They aren't sitting at a small dinner table.
What are they doing?
They are standing in the far corners of a massive ballroom.
That's a great visual. I can see that.
And because of that huge separation and the specific angles between them, there is very, very little commercial demand to fly directly across the center of Antarctica.
So almost no one needs to go from, say, Perth to Buenos Aires in a straight line.
Very few. The demand is usually to go north first to the major hubs, Dubai, Singapore, Los Angeles, and then connects from there.
But there are those flights, like Sydney to Santiago. I've seen those on the tracking apps. They go pretty far south, don't they?
They do. We call those the edge cases. They'll dip down to about 60, maybe 70 degrees south latitudes.
No, they get close.
They get close. They skirt the coastline of Antarctica to catch the benefit of the Great Circle route, but they rarely need to cross the deep interior, the high plateau. The geometry just doesn't require a full crossing of the South Pole to connect the major southern cities efficiently.
Okay, so reason number one is just practical geography. We don't fly there because, for the most part, we just don't need to.
That's the foundational economic reason, yes. But let's play devil's advocate.
Okay.
Let's say you did want to. Let's say a billionaire charters a jet and says, I don't care about the economy, fly me across the dead center of Antarctica.
Right, I want to see the pole.
Exactly. Now you run headfirst into the physical realities.
And this is where it gets really interesting. Section 2, the triple threat of Antarctic weather.
And I want to be clear here. Weather in Antarctica isn't just bad weather, like a thunderstorm or a blizzard. It's a different beast entirely. It is actively hostile to mechanical life.
Hostile to mechanical life. I like that.
And the first threat is something most people don't think about. It's not the snow or the wind. It's the temperature. Specifically, what that temperature does to jet fuel.
Okay, ELI 5. This for me, explain. Like, I'm 5. Planes fly at 35, 40,000 feet all the time. It's freezing up there.
It is.
It's minus 50 degrees Celsius over Dubai when you're at cruising altitude. Why is Antarctica any different?
That is the most common question I get. It's cold everywhere up high, so what?
Yeah.
Here's the difference.
Okay.
Over the Antarctic interior, specifically during the polar winter, the stratosphere gets colder than anywhere else on the planet. We are talking about ambient air temperatures dropping to minus 80 degrees Celsius or lower. The record low on the ground at Vostok Station is minus 89.2 degrees.
That's hard to even comprehend. That's colder than Mars sometimes.
It is. And it creates a massive, massive problem for the fuel. Commercial airliners use a standard fuel called Jet A, or Jet A1.
Right, it's basically kerosene.
Essentially, yes. And a good analogy is to think of it like olive oil in your fridge.
Okay.
If you put olive oil in the fridge, it doesn't freeze into a hard block immediately, but it gets cloudy, it gets thick, it gets sludgy.
Yeah, congeals.
Right. Jet A1 begins to freeze, or more accurately, it begins to wax at around minus 47 degrees Celsius.
Wax. Like a candle.
Literally. Paraffin wax crystals begin to precipitate out of the liquid. It turns into a gel. And if you have wax crystals floating in your fuel, they hit the filters and they clog them.
And if the filters clog?
The fuel stops flowing to the engines. If the fuel stops, the engines stop. And then you are in a very large, very heavy, very expensive glider.
Which sounds suboptimal. But wait, don't planes have heaters for the fuel?
They do. They have what are called fuel oil heat exchangers. They take the hot oil from the engine, which is hot because, it's a jet engine, and they run it near the fuel lines to warm the fuel up before it burns. It's a very clever passive system.
But it has limits.
Huge limits. Those systems are designed for standard cold, minus 50, maybe minus 60 degrees for short periods. They're not designed for a sustained flight at minus 80.
Okay.
If you were flying over the Antarctic plateau for 10 hours in minus 75-degree air, you get what's called cold soak.
Cold soak?
The entire structure of the wing, and remember, the fuel is stored inside the wings, become so thoroughly chilled that the heat exchangers just can't keep up. The fuel temperature drops and drops, and you risk flaming out both engines at the same time.
Is there a solution to this? Is there an Antarctic mix of fuel or something?
There is. It's called Jet B. It's a naphtha-kerosene blend that stays liquid down to minus 60 degrees Celsius. They use it in parts of northern Canada, for example.
So why don't we just use that?
Because commercial airlines don't carry it.
Why not?
It's incredibly volatile. It's dangerous to handle. It has a much, much lower flash point than Jet A. Most major airports, Sydney, LAX, Heathrow, they don't even stock it because of the fire risk.
So you can't just pull up to a gate in Los Angeles and ask for a tank of Jet B for your special trip.
Absolutely not. So you're stuck with Jet A1, which literally might turn to jelly over the South Pole.
Okay, so the fuel is trying to freeze. That's threat number one. What's threat number two?
The wind.
And the sources were very specific here. They didn't just say it's windy. They used a specific term. Katabatic winds.
Katabatic. It comes from the Greek word for descending. And this is pretty unique to the geography of a place like Antarctica or Greenland.
Okay.
Antarctica is a dome of ice. The center of the continent is actually very high altitude. We're talking miles high. The air on top of that dome gets super chilled.
And cold air is heavier than warm air.
Exactly. It becomes dense, heavy. So gravity just pulls it down the slopes of the ice cap toward the coast.
So it's not a normal weather system wind?
No, it's not driven by high and low pressure systems like a normal wind. It's driven purely by gravity.
It's like an avalanche of air.
That is the perfect metaphor. It flows like water, accelerating as it goes down the slope. And by the time it hits the coast, these winds can exceed 300 kilometers per hour.
Wait, 300? That's a Category 5 hurricane.
It is. The Australian Antarctic Program reports from Mawson Station mention gusts of 244 kilometers. They talk about these winds moving fully laden shipping containers.
Moving shipping containers.
Imagine a 20-foot steel box full of gear just sliding across the ice because the wind is pushing it.
And if you're a pilot, turbulence is one thing, but that sounds like, I don't even know what that is.
It's severe mechanical turbulence. And on the ground, it creates these ground blizzards. Even if the sky above is crystal clear, the wind is picking up all the loose snow and blasting it horizontally. If you had to make an emergency landing in that, the crosswinds alone could just flip a commercial airliner right over.
Which brings us to threat number 3. Let's say you manage to keep your fuel liquid, you fight the hurricane winds, and you look out the window to land, and you see nothing. The whiteout.
And we need to be really clear to distinguish this from fog. Fog is just a cloud on the ground. You can see through it eventually.
Right.
A whiteout is an optical phenomenon. It happens when you have an unbroken, featureless snow cover on the ground and a uniform, overcast sky above.
So you have a white floor and a white ceiling?
Exactly.
Right.
The light just bounces back and forth between the snow and the clouds. It diffuses perfectly. And the result is you lose all shadows, you lose the horizon, you lose all sense of depth perception.
It's like being inside a light box or giant soft box.
That's what pilots say. They describe it as flying inside a ping pong ball. You literally cannot tell where the air ends and the ice begins.
So you could be descending thinking you're 1,000 feet up.
And you're actually 10 feet from the ground. Or you could be flying straight towards a mountain and your eyes would tell you nothing. It's sensory deprivation at 500 miles an hour.
That is terrifying.
It is. So you have fuel that gels, winds that move shipping containers, and an environment that completely blinds you. That is the weather slice of our Swiss cheese model.
And yet, we do fly over the Arctic. We fly over Siberia. It's cold there too, so there has to be something else holding us back.
There is.
And this brings us to Section 3, the regulatory wall. We kept seeing this acronym in all the sources. ETOPS. ETOPS.
ETOPS. This is the golden rule of modern long-haul aviation. Originally, it stood for Extended Range Twin-Engine Operational Performance Standards.
That's a mouthful.
It is. So in the aviation world, the joke is that it stands for engines turn or passengers swim.
Engines turn or passengers swim. I love aviation humor. It's so perfectly dark.
It has to be.
Yeah.
But essentially, ETOPS is a rule about time. Most modern long-haul planes have two engines. Think of the Boeing 777, the 787, or the Airbus A350.
The twin jets.
Right. They're incredibly reliable. But at the end of the day, engines are machines, and machines can fail.
Okay.
So if one engine fails, the plane can fly perfectly fine on the other ones, designed to do that. But it's not efficient, it flies lower and slower, and it is considered an emergency situation. You want to get that plane on the ground as soon as you safely can.
So the regulation sets a timer on that.
Exactly. The regulations say that your flight path must always be within a certain flying time at that single engine speed of a suitable diversion airport.
Okay. So if I'm flying from New York to London and an engine blows out halfway across the Atlantic, I have to be able to limp to where? Newfoundland, Iceland, Ireland.
Precisely. Gander, Keflavik, Shannon. You have options. The ratings tell you how far away you can be. ETOPS 120 means you can be 120 minutes, 2 hours from an airport. ETOPS 180 is 3 hours.
And what are the modern planes at?
The modern planes have incredible ratings. The 787 has ETOPS 330. Some A350s are rated for ETOPS 370.
So that's 5.5, even over 6 hours from an airport. That seems like a really long time. That should cover Antarctica, shouldn't it?
You'd think so. If you fly right over the pole, you might be within 5 hours of, say, Christchurch in New Zealand or Punta Arenas in Chile. Geographically, you might be in range. But remember the exact phrase, suitable diversion airport. That's the kicker. That is where the entire plan just falls apart.
What counts as suitable? I assume it's more than just a strip of flat ground.
A lot more. It means a runway that is long enough and strong enough for a heavy jet. A runway that isn't made of soft snow. It means having the right emergency equipment, fire trucks, de-icing gear.
And people. And buildings.
And ideally, a place where you can put 300 stranded passengers without them freezing to death in an hour.
And Antarctica has none of that.
Effectively, yes.
Right.
Look at the Arctic comparison again. You have Anchorage, Fairbanks, Svalbard in Norway, Keflavik in Iceland, Iqaluit in Canada. These are real, certified commercial airports with paved runways, instrument landing systems, terminals, hotels.
Right. Infrastructure.
In Antarctica, you have research stations. McMurdo has a runway, but it's an ice runway. Casey Station has a runway, but it's gravel and ice. The Troll Station has one. But these are not certified commercial airports.
And are they even open all the time?
No, that's another thing. They're often seasonal. They might be completely unstaffed or unreachable during the polar winter. They don't have hangars big enough for a 787. They don't have Hilton down the road.
Right. I was reading in the NASA safety reports about a dispatcher who got distracted and almost routed a flight into a non-compliant zone over the pole. It just shows how easy it is to make a mistake and how few options you have.
It's true. So let's say you're flying over the pole, you have an engine fire. Where do you go? The weather at McMurdo is bad, which we just established it usually is, so you can't land there. Suddenly, you are legally and, more importantly, physically out of options.
So the airport void is the real deal breaker.
It is the hard regulatory wall. You simply cannot fly where you cannot land safely in an emergency. It's the most fundamental rule of aviation safety.
Which segues perfectly into our next nightmare scenario. Let's say you ignore the rules. You fly over the center. You have that double engine failure because the fuel gelled. You manage an incredible feat of airmanship and crash land the plane on the ice. Miraculously, everyone survives the impact. Now what?
Right.
Section 4, the nightmare of rescue.
This is where we look at those mass rescue operations, or MRO reports from COMNAP. They hold workshops on exactly this what-if scenario, and the conclusions are, frankly, terrifying.
I'm guessing it's not like crashing in the Hudson River where the ferries are there in 5 minutes.
Not quite. The primary search and rescue assets, the ice-strengthened ships, the long-range helicopters, are mostly stationed in what they call the gateway cities.
So, Christchurch, Cape Town.
Christchurch in New Zealand, Cape Town in South Africa, Hobart in Tasmania. These places are thousands and thousands of kilometers away from the continent's interior.
So if I crash, how long am I waiting? Seriously.
If a ship has to be dispatched from one of those gateway cities, you are looking at 5 to 6 days.
5 days on the ice.
5 or 6 days, best case. If there happens to be a research vessel nearby, maybe you get lucky. Maybe 24 to 48 hours.
Won't be.
But remember, even that vessel might not be polar code compliant. It might not be ice strengthened. This is the Southern Ocean. It's full of pack ice. A normal ship can't just drive through it. They might get within 50 miles of you and then get completely stuck.
And what if you don't make it to the ice? What if you go down in the Southern Ocean?
Then it's over. Survival time in those water temperatures is measured in minutes. We're talking maybe 30 minutes before hypothermia makes you unconscious.
Yeah.
You'd perish long, long before any rescue could even be launched.
The logistics report also mentions something about the medical capacity at the bases.
Yes. This is a huge factor. Let's say you have 300 survivors on the ice. Maybe 50 of them have broken bones, severe burns, internal injuries. The research stations, McMurdo, Scott Base, Amundsen Scott at the Pole, they have tiny clinics.
Not hospitals?
No, clinics. They have 1 or 2 doctors. They're set up to handle a broken leg from a fall, or an appendicitis.
Actually, I read this one detail that just stuck with me. One of the sources mentioned that some Antarctic programs require their winter overstaff to have their appendix removed before they deploy.
Yes, that is true for some of the more isolated stations. It just illustrates how extreme the medical isolation is.
Wow.
If they can't handle a single routine appendectomy, they certainly cannot handle a mass casualty event with 200 injured people arriving at their door. They don't have the blood supply, they don't have the beds, they don't have the surgeons.
There was a case study in the COMNAP reports that really drove this home for me. The fire at the Chilean base, Bahia Fields.
Yes, this was a real event. A fire broke out at a station. Now, keep in mind, this is on the ground. You have trained personnel, you have firefighting equipment right there. But they couldn't put it out.
Why not?
The water in the fire hoses froze solid.
Oh my God. You're kidding.
And the high winds, those katabatic winds we talked about, fanned the flame so hard it was completely uncontrollable. They had to evacuate the entire station. Now, apply that scenario to a crashed, burning Boeing 777. The wreckage is on fire. You try to use fire extinguishers, but the foam freezes. The wind is 100 miles an hour. It is a completely hopeless situation.
It really paints a picture of why the regulations are so strict. It's not just bureaucracy.
It's not bureaucracy at all. It's survival. It's a concept in safety called normalization of deviance. If you start bending the rules, soon the bent rule becomes the new normal until a disaster happens, so you have to be rigid.
Right. Okay. So we've talked about weather and rescue, but there's another invisible force at play down there. Section 5, navigation and the ghost of Mount Erebus.
Right. We have to talk about magnetism. We all learn in school that a compass points north. But when you get very close to the magnetic South Pole, the magnetic field lines aren't horizontal anymore, pointing you in a direction along the ground. They are vertical. They're diving straight down into the earth.
So your compass just, it spins around.
It becomes incredibly unreliable. It fluctuates wildly. It just wants to point down.
But modern planes don't really use magnetic compasses anymore, do they? It's all GPS.
They primarily use GPS and inertial reference systems, which are incredibly accurate. But aviation law, for very good reason, requires redundancy. You need backup systems. And if your primary magnetic backup system is spinning in circles, that's a significant problem. It removes a layer of safety.
But people did fly there. Before all these rules were so strict, we have to address the elephant in the room. The tragedy that really stopped commercial Antarctic flights for a generation.
Air New Zealand Flight 901.
The Mount Erebus disaster.
November 1979. This is absolutely crucial to understanding the industry's deep-seated hesitation. Back in the 70s, Air New Zealand and Qantas ran these sightseeing flights over Antarctica.
It sounds amazing, honestly.
By all accounts, it was. They were huge parties in the sky, champagne flowing, flying low over the ice, the pilots pointing out the landmarks. A huge adventure.
Until it wasn't?
Until Flight 901. It was a DC-10. It had 257 people on board, passengers and crew. They were flying toward Ross Island, which is home to Mount Erebus, a 12,000-foot active volcano.
And they crashed right into it.
They flew straight into the side of the mountain. Everyone died instantly.
How does a modern airliner, even in 1979, fly into a volcano in broad daylight?
It was a fatal combination of two things. First, a computer error. A navigational coordinate in the flight plan had been changed on the ground the night before, but this change was never communicated to the flight crew.
So they were off course and they didn't know it.
Exactly. The computer was taking them about 27 miles east of where they thought they were. They thought they were flying down the middle of the wide, flat McMurdo Sound.
But they were flying directly towards a mountain.
Directly towards the slopes of Erebus. And this is where the second factor comes in. The sector whiteout we discussed.
The ping pong ball.
The pilot, Captain Jim Collins, was very experienced. He looked out the window. He saw white snow below. He saw white clouds above. And in between them, the white snow-covered slopes of Mount Erebus blended in perfectly. The mountain was invisible.
He thought he was flying over flat ice.
Yes. There was no contrast, no shadow, no horizon. The ground proximity warning system started blaring, "Pull UP, pull UP," but by the time it did, it was 6 seconds to impact. There was no time.
That is just heartbreaking.
It was a watershed moment for aviation. It ended all Antarctic tourism flights for decades. It proved in the most tragic way possible that visual flight rules, just looking out the window, do not work in Antarctica. And it proved that a tiny navigational error, which might be an annoyance over the Atlantic, is absolutely fatal over the Antarctic.
So we have the ghost of Mount Erebus hanging over this whole topic, and yet, Section 6, the exceptions. Because you can buy a ticket to fly over Antarctica today, can't
You
you?
can. Qantas resumed these flights a while back, and they are fascinating operations. They're branded as Antarctica flights.
I looked these up. They use a Boeing 787-9 Dreamliner. They take off from an Australian city, Sydney, Melbourne, Perth. They fly for 12 to 14 hours, loop over the continent for a few hours, and then land back at the same airport they left from.
The ultimate flight to nowhere.
Exactly. So how do they get around all the problems we just spent the last hour listing? The fuel, the ETOPS, the lack of rescue.
Well, a few clever ways. First, they carry massive amounts of reserve fuel. They aren't trying to get from point A to point B so they can just load up on gas. They have fuel for the entire round trip, plus huge reserves.
So the fuel gelling isn't as much of a risk if you have that much extra.
Correct. Second, they never land on the ice, so they don't have to deal with the ground blizzards or the ice runways. And critically, they treat it as a domestic flight.
A domestic flight
Right.
when it goes to another continent.
Because it takes off and lands in Australia, you don't even need a passport. But the safety protocols are intense. They have polar survival kits on board. They have multiple specially trained flight crews. And, of course, they have that modern ETOPS 330 rating on the 787, which allows them to fly flight paths much deeper and safer than the old DC-10s ever could.
I read about the seat swap. This made me laugh.
Oh, the logistics of a fair viewing experience.
Yeah. So you pay a lot of money for these tickets, but if you're in the cheap seats, in economy standard, you might be over the wing. So halfway through the flight, the crew gets on the PA and makes everyone swap seats. The person at the window has to move to the aisle, and the aisle person gets the window for the second half of the viewing. It's like musical chairs at 30,000 feet.
It sounds chaotic, but it works. The reports say passengers stand in the aisles. They treat it like a cocktail party. It's a very different vibe from a scheduled transport flight where everyone's just trying to get somewhere.
There was also a specific incident recently that the sources mentioned, Qantas QF-28. This wasn't a sightseeing flight. It was a scheduled one from Santiago, Chile to Sydney, and it went deep.
Yes, I remember this. Usually that flight path stays around 70 degrees south. But on this particular day, they had massive headwinds, incredibly strong winds pushing against them.
Which burns more fuel.
A lot more. To avoid having to divert or run low on fuel, they made a decision to find a shortcut. They pushed their route down to 74 degrees south.
Into the danger zone.
Into the deep Antarctic. And they could only do that because the 787 is such a capable, modern machine with that long ETOPS rating. It proves that technology is slowly opening the door. But notice, they only did it to avoid a worse problem, the headwinds. It wasn't their preferred route.
And then, of course, you have the people who actually do land there, the military, the scientists.
The pros?
The pros. The ski birds. The LC-130 Hercules, these are tough, four-engine, propeller-driven military cargo planes, and their special trick is they're equipped with massive skis instead of wheels.
So they can land on snow. They can land on unprepared snowfields. And then you have the giant C-17 Globemaster jet, which can land on the Blue Ice Runway near McMurdo Station.
What's a Blue Ice Runway?
It's a section of the ice cap where the wind has blown away all the snow, leaving just ancient, super compacted ice. It's so hard and dense it acts like concrete. But they have to carve grooves into it with a special machine so the jet's tires have some friction to grip.
That is just extreme aviation.
It is. And then you have the private charters, companies like White Desert, flying wealthy tourists on business jets. But again, these are not commercial airlines in the traditional sense. These are highly specialized, high-risk, very high-cost expeditions.
So let's bring this all together. We started with the question, why is there a big empty hole on the flight map?
And the answer is the Swiss cheese. All the holes line up.
It's the geometry. We don't really need to go there.
Right.
It's the weather. The fuel wants to turn into jelly. The wind wants to flip the plane. And the air itself wants to blind you. It's the infrastructure. There are no suitable airports to save you if something goes wrong.
The airport void.
And it's the rescue. If you do go down, you are on your own for at least a week.
And that void on the map, when you really understand why it's there, it represents a triumph.
Really? A triumph? How so?
It's a triumph of safety culture. We could fly over Antarctica. Technologically, we have the planes to do it. We have the pilots who could handle it. But the entire global aviation industry, the regulators, the airlines, have looked at that void and collectively said, the margins are too thin. The risk is too high.
We choose not to.
We choose not to. We choose safety over a shortcut. That blank spot is there because we, as a civilization, decided that human life is worth more than saving 2 hours on a flight from Perth to Buenos Aires.
That is a really powerful way to look at it. It's not a failure of technology, it's a success of risk management.
Yeah.
So here is my final provocative thought for you to chew on. We've talked about how technology is constantly improving. Electric planes are on the horizon, better batteries, more efficient engines. And we know the climate is changing. The sea ice is melting, which could change weather patterns.
True.
Will the Forbidden Zone eventually open up? Will we see a Delta or a British Airways flight cruising over the South Pole in, say, 20 or 30 years? Or will Antarctica remain the last place on Earth that humans simply agree to leave alone?
It's a fascinating question. Historically, as technology advances, the impossible tends to become the routine. But having read about the sheer raw ferocity of those katabatic winds, I wouldn't bet on it happening anytime soon. Some things are just hostile.
I think I'll stick to the window seat on the flights going north for now. Thank you so much for breaking all this down with us.
My pleasure. Fly safe.
And to you listening, next time you're on a long flight, look at the map on the screen in front of you. Appreciate the lines, sure, but maybe appreciate the empty spaces even more. Thanks for listening to The Deep Dive.